Hello everyone, my name is Rohini and I'm presenting a survey on algorithms in energy harvesting embedded systems based on task scheduling. These are the contents of my presentation, which include introduction, earliest deadline with energy guarantee, earliest deadline feedback scheduling with energy guarantee, load matching adaptive algorithm, utilization based mapping algorithm on multi-core systems, semi-dynamic algorithm, and the conclusion. Introduction. What is energy harvesting? Energy harvesting is a technique to convert the ambient energy into electrical energy. The requirement of self powered devices is rising as there is a need to power mobile and sensor networks without using batteries. It has various advantages. The advantages are that it increases the lifetime of energy constrained systems and it uses renewable sources of energy. The first algorithm is earliest deadline with energy guarantee EDEG. EDEG is an improved version of classical EDF algorithm and schedules the task as per the EDF algorithm. A task in EDEG is considered to consume energy with any power such that there is sufficient energy storage to execute the task for at least one time unit. The processor will remain idle in cases where there is insufficient energy. The three main parameters of EDEG are E of t, which is the energy presently stored at time t. Slack time. Slack time at current time t is the length of longest interval starting at t during which the processor can be idle while still completing all the timing deadlines. Slack energy. It is the maximum amount of energy that can be consumed from a given time t while still completing the timing and energy constraints of all the future occurring tasks. The performance evaluation of EDEG is implemented and tested on C++ simulators. It is implemented and tested for low and high energy utilization based on the following three aspects, which is percentage of feasible tasks, average idle time, and time overhead. For low energy utilization, the system is set to consume small amount of energy as compared to the energy stored by harvesting. The task sets are compared for EDEG and EDS algorithms. Figure 1 shows the percentage of feasible task sets with various processor utilization, that is 0.3, 0.6, and 0.9. When the processor utilization is 0.3, all the tasks are feasible under the EDEG algorithm and the energy is approximately 7,100 units. EDEG uses the idle time to recharge the battery whenever the energy storage is insufficient to execute the future tasks. Whereas EDS will need more energy storage than EDEG to guarantee feasibility, that is approximately 21,000 units. Therefore, it is clear that EDEG can provide the same performance with a storage unit that is 4 times less than the EDS. For 0.6 and 0.9, the relative performance gain of EDEG in terms of capacity savings decreases when the processor utilization rate increases. Lower the number of idle time intervals, lower energy is used for turning the processor from the state of inactive to active. The second figure shows the comparison of idle time of EDEG and EDS. The average idle time of EDEG is greater since the total number of idle times is less. The third figure shows the time overhead, and as it can be seen in the figure, the time overhead increases with the increase in the processor utilization. Hence, more the processor utilization, more the time overhead. Following are the results of experiments which were conducted with high energy utilization. From the figure 1, that is the percentage of feasible tasks, it can be inferred that the relative performance gain of EDEG in terms of capacity saving decreases when the processor utilization increases. From the second figure, that is the average idle time, it can be said that the total number of idle time for EDEG is lesser than the other two techniques. For higher energy utilization, the consumption of energy increases and hence the number of lower battery level increases. Thus, the number of idle times increases and consequently the average idle time decreases. The third diagram is of time overhead. It is seen from the figure that the processor utilization increases the time overhead till it reaches a maximum value of zero point 0.9. Time overhead for harvested energy utilization ultimately increases. The second algorithm is earliest deadline feedback scheduling with energy guarantee. This algorithm is an enhancement of EDAG algorithm and is improved by adding a feedback to the EDAG algorithm. The EDAG fails to perform in worst case execution times and hence the feedback is applied to improve the performance. The performance of this algorithm is evaluated in a simulator named TrueTime. Performance is evaluated on the rate of missed deadlines and the average and minimum energy available. It can be seen from the first figure that the rate of missed deadlines is considerably reduced by the use of this algorithm. And from the second diagram, it can be inferred that this algorithm saves a considerable amount of energy where the average energy is near to the maximum capacity of the battery. The third algorithm is load matching adaptive algorithm, LMAPM. It addresses the load matching problem through adaptive task scheduling and DVFS, that is dynamic voltage and frequency scaling. It considers realistic battery charging discharging overhead during runtime, and it helps to improve the system wide energy efficiency. A discrete C++ simulator is used to evaluate the performance of this algorithm. The following figure shows the comparison of deadline miss rates of ASDVFS and LMAPM. Experimental results show that LMAPM improves the system-wide energy efficiency by load matching and reducing operation overhead. Naturally, the improved energy efficiency leads to the lower deadline miss rate. The next algorithm is utilization-based task mapping for multi-core systems. This algorithm provides better efficiency in utilizing harvested energy as it selects the execution speed based on the CPU utilization, that is the lowest possible speed. It also distributes the task to all the cores, which minimizes the usage of overall system energy. Performance evaluation of UTB. A discrete event simulator in C++ is used to evaluate the performance. The graph below shows the deadline miss rate for various cores ranging from 1 to 3 and 1 to 4. It can be seen from the graph that UTB considerably reduces the deadline miss rate compared to the other two algorithms, which are random partition and task movement algorithm. The next algorithm is semi-dynamic algorithm. SDA is an algorithm well suited for multi-core embedded systems. It provides energy budgeting which can manage workload and energy distribution for the multi-core embedded systems. Performance evaluation. A discrete C++ simulator is used to evaluate the design. The performance of SDA is compared to UTB, and it can be seen from the figure that SDA consistently has lower rate of deadline miss irrespective of the increasing number of cores. Conclusion. Energy harvesting is an emerging field. The area of energy harvesting is being researched since the last decade and has achieved significant results in task scheduling. Of all algorithms compared above, semi-dynamic algorithm provides efficient results and better reduction in deadline miss rates for multi-core systems as compared to the previous work.